So I wanted to talk about Solubility Product. Which is basically a kind of another equilibrium constant. Now, this solubility product is whenever you dissolve something, it's in equilibrium. It's known as KSP. So whenever you, and this is about it's mostly about ionic products, ionic substances, ionic compounds. So whenever ionic compounds or substances they dissolve, it's about their solubility. What are ionic compounds? Ionic compounds are a bunch of positive and negative ions. Just one second. Maybe there's a nice Google image of ionic compound dissolving. Just one second. So ionic compounds dissolving in water. This is what is actually happening. Uh, this image is fine. Just one second. So this is what happens when ionic compounds they dissolve or mix in water. You've got a bunch of positive and negative ions. It's a crystal structure. It's a giant ionic lattice. So you've got sodium chloride over here, uh, which is obviously a giant ionic lattice. So it's a bunch of positive and negative ions that. So it's a bunch of positive and negative ions all strongly attracted to each other. What happens is when you vigorously stir them in water, what happens is that the negative ions and the positive ions, they all dissociate. So, so the negative and positive ions they break away. Okay, imagine you vigorously stirring this, and all the positive and negative ions they dissociate, and they mix. They get surrounded by water molecules. Now, the positive and the negative ions are still attracting each other, but there are lots and lots of water molecules that are coming in the way, which is why they're not able to attract each other. But some of them in a saturated solution, uh, imagine you're trying to add a salt to water, like NaCl to water, and you keep on adding salt to water. Eventually, the solution becomes saturated. A saturated solution means that no more salt can dissolve. In reality, what happens is that salt will continue to dissolve. Imagine you've added 1 spoon in a glass of water, then you've added a second spoonful of salt in a glass of water, then you're trying to add the third and the fourth spoon. So you're continuously adding. There would come a point when the salt would stop dissolving because the ions would become very close together. The concentration would become really high. And if the ions become really close together, what would happen is that the positive and negative ions will start to join up because they would be so close together and they would start forming the crystal back again. So it's going to become a reversible reaction. Like once the solution becomes saturated, if you try to dissolve more salt, NaCl solid, you try to dissolve more of it, it will dissolve, it will dissociate, but at the same time that the concentration of the ions would become so high that the ions would join up to form the salt crystal back again. So it's going to become a back and forth reaction. That's the point when no further salt is able to mix in water. So is this clear?
Yes,
Yes.
sir.
Okay, so salt dissolves up to an extent, beyond a certain extent until the solution is dilute. When it becomes very concentrated, the particles are really close together. They start joining up, and the reverse reaction also starts. So once a solution is saturated, remember this is only true for a saturated solution. If it was a dilute solution, then the reverse reaction would not be happening. The particles would be so far away that the chances of them getting to form the crystal back again would be very low. So it's only true for a saturated solution. Uh, so the reaction has now reached a dynamic equilibrium. And since it is an equilibrium, there's going to be an equilibrium constant. The equilibrium constant is going to be product concentration, which in this case is Na plus 1 into Cl minus 1 concentration divided by the reactant concentration. The reactant concentration in this case would be NaCl solid. Now we know that solids have constant concentration. I mean, their concentration is constant. So you don't write solids in the expression. So what you do is you either remove the solids, you take it as 1. So solids have constant concentration. Remember what concentration is. Concentration describes the spacing of the particles. So in solids, the spacing of the particles is fixed. In a solution, the spacing of the particles, they could be very far away, so it could be dilute, or they could be very close together, and that would mean it's concentrated. So in aqueous solutions, the spacing changes, but in a solid, the spacing never changes. So NaCl solid is always going to have a fixed concentration, which is taken as 1. Or in other words, you don't write it in the expression. What you state is that you take the two constants together. The NaCl solid concentration is also a constant, and you call this Ksp. So Ksp is Na plus 1 concentration into Cl ion concentration. That is what Ksp stands for. So basically, or if whichever you like to see this, you don't write NaCl solid concentration in the expression. So it's the product of the ions that are present in water. That is what Ksp is. So we're going to work on the expression first. The unit in this case is going to be mole squared. It's concentration times concentration, so it's mole squared dm minus 6. So I'm going to do another example of this. Now this other example is, let's talk about aluminum hydroxide dissolving. So you've got aluminum hydroxide, which is a solid. It's going to dissolve. It's going to produce aluminum ions, and it's going to produce 3 OH ions, and they are going to be in aqueous state. And if the solution is saturated, in a saturated solution, no matter how much you try to dissolve, the same, because the ions the solution would be so concentrated and the ions would be so close together that they would get together to form the solid back again. So it's going to be at equilibrium if it's saturated. The Ksp in this case is going to be products over reactants. The reactant is a solid, so it's 1. So it's just products, which is aluminum ion concentration multiplied by the OH ion concentration, and that's going to be cubed. And the unit in this case would be mole per dm cube to the power 4. So it's going to be mole 4 dm minus 12. Is this clear?
Sir, how will it be 4?
It's concentration into concentration cubed, like mole per dm cube into mole per dm cube cubed. So it's x to the power 4. Is this clear?
Okay, sir.
Actually, the next one, let's try another one. Let's now do aluminum phosphate. So aluminium phosphate is not aluminium phosphate. Let's do aluminium sulfate. It's a solid. We are trying to dissolve it. So it's going to produce. I've messed this up. Just a second. So it's Al2SO4 thrice. So it's going to produce two aluminium ions, aqueous, and three sulfate ions, and they would also be aqueous. Now, if you write the expression is going to be products over reactants. The reactant is a solid, so that's taken as 1. So it's just aluminium ions. That's going to be squared, and sulfate ions, and that's going to be cubed, and the unit is going to be mole 5, dm minus 15, I think. It's going to be concentration squared. This is power 3, sorry. So it's going to be concentration squared into concentration cubed. So basically it's concentration to the power 5. So that is what your expression for KSP is. Now, also remember KSP is going to be a constant. It's an equilibrium constant. So KSP is a constant. Every salt is going to have a very specific, the name has the word constant. It's a constant. It only changes with temperature. All equilibrium constants are going to change with temperature, and it would depend whether it would increase or decrease, because it depends if it's dissolving a substance is endothermic, then at higher temperature. So you're going to look at enthalpy of solution. Like if enthalpy of solution is endo, like if you're trying to dissolve a salt like a table salt and it requires energy, then it's going to be more soluble at higher temperatures because it requires heat. Vice versa, if enthalpy of solution is exothermic, so dissolving a substance produces heat, then it's going to be more soluble at lower temperatures. You need to remove heat. I say anyway, so KSP is constant, only changes with temperature. Now the first question is question type 1. And remember, focus on the term saturated. It's only for saturated, not for dilute solution. I'll write this down. KSP is calculated only for saturated solutions. For saturated solutions. Now, question type 1 is that you'll be asked to calculate KSP. So, for example, they might say that 500 cm cube solution, or phrase it the other way. Like I've got 2.5 grams of MgOH2 is dissolved in 500 cm cube solution. So they're asking you about and the solution becomes saturated. To make it saturated. So after dissolving 2.5 grams, no further MgOH2 dissolves. You're supposed to calculate KSP for this. Now, the first thing is you're going to figure out the solubility. Solubility is the concentration of the solute, and it's either given in mole per dm cube or sometimes in grams per dm cube, which is kind of the same thing because you can change grams to moles by simply dividing by mr. Uh, so remember that as well. Like if they give you something in grams per dm cube, like this many grams dissolve in a certain amount of water, you can always convert or divide by mr. Remember, mass divided by mr gives you moles, so the grams would become mole per dm cube. Is this part clear?
Yes.
Yes, sir.
Okay, so don't get confused if they give you grams per dm cube. Just divide by mr. Grams converts into moles. So the first thing is you calculate solubility. So it's 2.5 grams. How many moles is this? So I'm trying to find the concentration. Moles of MgOH2. Concentration is moles divided by concentration is moles divided by volume, which is in this case 0.5 dm cube, I think. So how many moles you've got? You've got 2.5 divided by what's the mr of Mg? That's 24. 17, that's 34. 34 plus 24, what do you get? 58. Can somebody double check this?
This is 58.
Okay, so you're getting 58. Use brackets, that's the moles, and divide this by the volume, which is 0.5 dm cube. So what's the concentration? Anyone, what do we get?
0.086.
Okay, so you're getting 0.08, right? What's the third one? Third significant?
2862.
Mole per dm cube. So this means this is the amount of salt that actually dissolves, MgOH2. So I'm going to write the equation of MgOH2 dissolving. So it's MgOH2 solid, and it dissolves, forms a saturated solution, forms Mg2 plus ions, aqueous, and forms two OH ions, which are also aqueous. Now the question is, I've got 0.0862 moles per mole per decimeter cube. I've got this. And I know this is the amount that's actually dissolving in the solution. So it's dissolving and dissociating to form these ions. Because he did say 2.5 grams dissolves. So this is the amount that's dissolving. So if one molecule dissolves, it produces one Mg2 plus. So the concentration would be of Mg2 plus would be exactly the same. It's going to be 0.0862 mole per decimeter cube. Is this clear?
Yes, sir.
And if one dissolves, it produces two OH ions. So the concentration of that would be double this. So it's going to be 0. What would it be? Can somebody double this?
0.172.
So we're getting 0.172 mole per decimeter cube. So we figured out that 2.5 grams in 500 cm cube dissolving, that means 0.0862 mole per dm cube is actually dissolving. So one dissolves, produces one ion and two OH ions. So if one dissolves, produces one of this and two of this. So we found the concentration of the ions in solution. We have those now. So I just need to put these values in the expression for KSP, and my KSP expression in this case would be product concentration divided by the reactant, which is a solid, so that's not going to be there. So it's going to be Mg2 plus into OH ion concentration, and the whole thing is going to be squared, right? So what do we get? I'm going to put in the values. It's going to be 0.0862. That's the first one. This one, and then it's going to be multiplied by 0.172, and that's going to be squared, right? Is this clear?
Yes, sir.
So find the value. What is KSP?
I get 2.55 times 10 to the power minus 3.
It's coming out to be 2.55 times 10 power minus. I'm not sure if somebody can double check this. It's and the unit is going to be mole cubed and dm minus 9. TK, is this clear?
Sir, it's correct.
TK. So that is how you're going to solve the question. That's one way of solving the question. So you're going to look for the concentration in the solution. In mole per dm cube, sometimes they use gram per dm cube. Don't get confused if it's gram per dm cube. Just divide by mr. That will turn into mole per dm cube. So that is how KSP is calculated. Now the other type of question that you're going to get is that the value of KSP would be known. So question type 2. KSP is known, and you have to do the opposite. You have to find the solubility in mole per dm cube. So it's exactly the reverse. So for example, I've got this salt, AgCl. So we're going to start off simple. I've got AgCl. And the value of KSP for AgCl is already with us. And that is 5.5 times 10 power minus 6. Mole square d minus 6. So this value is already present. So how do you find the solubility? Like how much is dissolving? Now remember, this is KSP value. So we're going to learn how to calculate KSP. Like KSP was calculated that you had AgCl solid and you were trying to dissolve it and it became saturated. So silver ions were produced, Cl ions were produced, and in a saturated solution, the more you try to dissolve, the ions would be so close together that they would form the crystal back again. So no further amount would dissolve. Now, we don't know how much it's dissolving. This is aqueous. So what we are not sure is how much is dissolving. So I'm going to say that what I'm going to state is, because I don't know how much of AgCl dissolves. So what I'm going to state is that X mole per dm cube dissolves. Okay, so I've put in X mole per dm cube of AgCl and it dissolves completely. I don't know what X is. So one dissolves, produces one of this. So that means if X mole per dm cube dissolve, they're going to produce X mole per dm cube of Ag plus 1 ions, and they're going to produce X mole per dm cube of Cl minus 1 ions as well. Right? Is this part clear?
Yes, sir.
So there's a question mark. We don't know how much of AgCl is actually turning into aqueous ions, how much of it is dissociating. So I just stated X. Now I can write the expression for KSP. The KSP expression is product concentration, Ag plus concentration into Cl minus 1 concentration divided by the reactant concentration, which is a solid, so you don't write that. So it's basically X mole per dm cube into X mole per dm cube. And we already have the answer. The KSP value is 5.5 times 10 power minus 6. So all I have to do is, X is the solubility, so it's X squared. So it's going to be 5.5 times 10 power minus 6 and the whole thing is going to be under rooted. So what do you get?
2.34 multiplied by 10 to the power minus 6.
2.34 multiplied by 10 power minus. Are you I don't think it's going to be minus 6. Can you try again putting a bracket around it? Should be around 10 power minus 3, I think. Like you're taking the remember you should immediately know if you've messed up on
Minus 3.
so it's going to be minus 3. Make sure the more you practice, always check your math. Like if you can just by looking at the answer, you can figure out if you've done something wrong or not. Like if you, even simple math, remember, don't trust your calculator. Never trust your calculator because you can make a lot of mistakes on your calculator. So if you're underrooting things, I mean, they always have this hint that the power is going to be divided by 2. I mean, that's what under root is. It's 1 by 2 basically. So it's going to be 6 by 2. So should be 10 power minus 3. If you're taking a cube root, remember that the answer should be minus 2 then because you're making it 1/3 now. So always have this idea, this hints about math, okay, whether you're doing the math correctly or not. So make sure along with doing calculators, always do some guesswork as well. So you're getting 2.34. That's your concentration. That's it. So that's the second type of question. That's it. Basically, you're going to get 2 types of questions. There's another thing called common ion effect. But let's do another type, a similar type of question. Okay, just remember that if Ksp is known, you're going to assume that you can assume any value, x mole per dmq is going to dissolve, and you'll find the concentration of the ions in terms of x. Put those in the expression and find. So let's do another one, which is going to be slightly more difficult, the same version. Okay, same type of question. So I've got the Ksp of a substance is given, and that substance is let's call it AlCl3. So we have the Ksp of AlCl3, and that value is 2 into 10 to the minus 3. Remember, it's just a hypothetical value. It's mole 4 dm minus 12, I think. So just a hypothetical value. AlCl3 dissolves. We need to find the concentration. Remember, he's asking for the solubility, like how much dissolves. What's the concentration in a saturated solution? Remember, he's going to use the term saturated. So I've got AlCl3 solid. I'm trying to dissolve it. The solution becomes saturated. So it's Al3 plus aqueous plus 3Cl minus 1 aqueous. Now I have no idea in a saturated solution how much AlCl3 is going to dissolve. So I'm going to assume that x moles per dm cube dissolves. So to make the solution saturated, I dissolved x mole per dm cube, and they all went into the solution and they dissociated. So one dissolves, produces 1 Al ion. So x dissolved, they're going to produce x mole per dm cube of aluminium ions. And one dissolves, produces 3 Cl ions. So the amount of Cl ions is going to be 3 times. So it's going to be 3x mole per dm cube. Is this clear?
Yes, sir.
And then you write the expression for Ksp, which is it's Al3 plus concentration multiplied by Cl minus 1 concentration, and it's going to be cubed. So I have the concentrations in terms of x. I have the Ksp value, so it's going to be 2 times 10 power minus 3. Al concentration is given as x, saline concentration is 3x. So it's going to be x into 3x, and that's going to be cubed. And you solve for x. So it's basically what? I think it's 27 x power 4, right? And this is 2 times 10 power minus 3. Get the 27 to the other side, and then take the fourth root of this. So what do we get for x? Has anyone done this?
Sir, it's 0.0927.
So x comes out to be 0.092
927.
mole per decimeter. 927, right?
Yes, sir.
So that is the concentration of AlCl3 that's actually going into the solution. So you found that value, that's it. So remember, the ratio is going to be different. So if you assume x, on the other side, the amount of ions are going to be in a different ratio. It's going to be x mole per dm cube. This would be 3 times that much. So that is going to be 3x. Then you put the same concentrations that you found out in the expression of KSP, and you solve for x. So is this clear to everyone?
Sir, just one question.
Yes.
Mole for dn minus 12. What do we have to do with that?
The thing is just the unit. I mean, I gave you the unit. It's like every time KSP is going to have a different unit. It's concentration times concentration cubed, right?
Yeah.
Okay, so every time whenever KSP is written, it's going to have a different unit depending on the salt. Okay, clear?
Okay.
So another thing about this is that there's a thing called the common ion effect, which I mean, we can do it. Just a second. So we have a common ion effect, and just one second. And I'll just quickly mention common ion effect, which is probably won't be able to complete this. The common ion effect is, like, most of the time you're assuming that there's only one salt in the solution, right? Like if you take drinking water, it has a lot of salts mixed in it. So if I try to dissolve NaCl, solid, and it produces Na plus 1 aqueous and Cl minus 1 aqueous. Now what if the solution already contained a lot of Cl ions even before you are adding NaCl? Okay, for example, you took tap water, the tap water had a lot of Cl ions. So if it already has a lot of Cl ions and the Cl ion concentration is very high, if you're trying to dissolve NaCl, where would the equilibrium shift if the Cl ion concentration is very high?
To the left.
Okay, so it's going to shift to the left, and that means NaCl the solubility would decrease, right? So you're going to have, so remember, it's an equilibrium reaction, and the equilibrium reaction can shift forward or backward depending on the concentration of the substances. So maybe your solution already had a lot of Cl ions, and you had a crystal of NaCl, and you try to dissolve it. it's not going to dissolve. The solubility would decrease. So I'm just going to write this solution already has a common ion. So equilibrium shifts backwards. It shifts backwards and solubility decreases. Right? Is this clear? Okay. I mean, is the concept clear?
Yes, sir.
So, and why are there CLI? I mean, remember, negative ion cannot exist alone. There might be another salt, like you're trying to resolve NaCl in a solution that has HCl in it. There's H plus one and there is Cl minus one. You already added HCl, so there's a common ion. The Cl concentration is already very high, so it's not going to mix. So remember, whenever you've got common ions, and the other problem is that these two ions are not going to have the same concentration. Like if NaCl dissolves, this is x mole per dm cube. Then the sodium ion concentration would also be x mole per dm cube. But the Cl ion concentration is not going to be x mole per dm cube because there's already Cl ions present even before you've added NaCl. So is this clear as well?
Yes.
Okay, so we'll continue with the common ion. Okay, there's just a little bit left. We'll do questions on this. Past paper questions the next class then. Okay. Let's continue next time. Any questions? No questions? Is this all clear?
Yes, sir.
Okay, take care everyone. Allah Hafiz.
Thank you.